All right, so we are starting section 14.7. This is the last section in chapter 14. And just like before, there will be an A and a B. Part A, we're going to focus on how to actually find maximum and minimum values, both relative and absolute, just like we would have in ABBC calculus. And then in part B, we're going to focus on the applications of those. So let's go ahead and talk about maxes and mins in 2 dimensions. Okay, this is something that's more of just a review. If we were to have some kind of a curve, whatever that curve is, and then we were to say this point right here is your C, well, right up here would be the location of your local max. And we would say simply that f prime of C equals 0, or the derivative or the slope there equals 0. So if that's the case, then x equals c will be a critical point. Will be a critical point. Okay, and we can actually say critical point there because it's an actual point on the graph, not just a critical value. So now let's go ahead and translate that into 3 dimensions. Excuse me. So if we put this into some kind of 3-dimensional perspective, and let's say that our surface now looks something like this. I'm not sure if I do that very well, but we're going to find out. No, I don't like it. Let's start off a different direction. Let's do this. There we go. Okay. Sorry. Kind of dash that. Oh, this is horrible. My drawing skills are not very good this morning. Okay, whatever. It's close enough. Probably should have stuck with the first one I did. In any case, on a surface, you're going to have your critical value at the top or at the bottom, wherever the surface is. And for a critical value to occur, both f sub x equals 0 and f sub y equals 0. So basically, the slope in both the x and the y direction has to equal 0. So a critical point in 3 dimensions is defined to be any point AB such that the partial derivative of x at the point AB and the partial derivative of y at the point AB equals 0. So both of those two things have to equal 0. Okay, it's pretty straightforward. Basically, we're just saying, okay, now we're in 3 dimensions. Now the derivative in both the x and the y direction both have to equal 0 for you to have a critical value, critical point. Not an extremely difficult concept. All right, so let's go ahead and take a look at an example. So we've got f of xy, which is x squared plus y squared minus 2x minus 6y plus 14. Determine the critical values of the function and determine if it's a maximum, minimum, or neither. So we can have a case of neither, and I will explain that one as we get to it. So the first thing that it said to do was, well, we have to take the partial derivatives and make sure that that equals 0. So let's take the partial derivative with respect to x, which is going to be 2x minus 2, and we have to set that equal to 0. Well, solving that, you would add 2 and divide by 2, then you would just get that x equals 1. We also have to do the same thing in the y direction. So the partial with respect to y is going to be 2y minus 6 Setting that equal to 0, add the 6 and divide by 2, you would get that y equals 3. So now we have a critical point. Our critical point is the point 1, 3. So now the question says, is that a max? Is that a min? Or is that neither? Well, in order to figure this part out, just like we did in calculus ABBC, instead of creating a little number line, although we're going to create a chart here, instead of creating a number line, we're actually going to use a second derivative test. So remember back in basically your Calc 1, Calc 2 stuff, if you wanted to determine whether something, here, let's look at this. If you wanted to determine whether something was a max or a min, you could tell that by the concavity. You could tell it by the second derivative. We know that this point right here was a critical value or a critical point, and because of the fact that it was concave down, it makes it so that it is a maximum. If it was concave up and you had a critical value, then you know it would have to be a minimum. Similar kind of idea here. In order to do this, we need to use the second derivative test. But the thing about the second derivative in 3 dimensions is that we have multiple second derivatives. So here's what we want to do. We want to let AB be a critical point. Okay, so obviously if it's not a critical point, this doesn't matter. The second derivative test is going to be determined by doing what we typically call the D test, where D simply stands for determinant. And we are going to take the determinant of all of the partial derivatives. So what are all the partial derivatives you could have? Well, I can have f sub x, that's a second derivative, both with respect to x. I can have f of x, y, which means I took the derivative first with x and then y. Or I could have f, y, x, which means I took the derivative first with respect to y and then x, or I could take both partials with respect to y. And you might be looking at this and saying, well, wait a minute, isn't fxy and fyx the same thing? Yes, they are. So when we write this, if you do your determinant, your determinant from this, it's going to be fxx times fyy minus the product of fxy, fyx, but they are the same thing. So we can write that basically as fxy or fyx, doesn't matter, squared. And so here is the actual test results. If D is greater than 0, we are going to have a max or a min. The test is if fxx is also greater than 0. Well, now let's think about that. So D being greater than 0 tells us that we have a max or min. The fact that the second derivative with respect to x's is positive is going to tell us that it is concave up, which means that we're going to have a minimum. If D is greater than 0, again indicating a max or a min, but this time fxx is less than 0, then what that's going to tell us is that it is concave down, meaning we have a maximum. And then the third case is if D is less than 0. If D is less than 0, we have what is known as a saddle point. And that would be the neither category. It would be neither a maximum or a minimum. And I'll try and explain the saddle point when we get to it. So now let's go ahead and use this test on our critical point. Our critical point is the point 1, 3. So it says, take fxx, multiply it by fyy, and subtract fxy squared. Okay, that's our D value. So let's go ahead and do that. The second derivative with respect to x. So now I have to take fxx, which is just going to be 2 in this case, times the second derivative with respect to y, which is also going to be 2 in this case. Now the second derivative with respect to x, second derivative of x with respect to y is 0. Likewise, the second derivative of y with respect to x is also 0. Again, they should be the same. Normally, we're going to write some more information out here, but since these all worked out to be nice, easy constants, there was not really much to write. So what you get, oh, that should be squared, although that's not going to make any difference, is 4. 4 is a value which is greater than 0, so we have a critical value. So all we need to say now is, what is the sign of fxx? Well, fxx is greater than 0 because it's 2, which means that this thing is going to be concave up, so we have a minimum. So our minimum is going to be at the point 1, 3, and then we have to find the z value. Could they give that to us? No, we have to plug that back in. If you plug 1 and 3 back in, you're going to get 1 plus 9, which is 10, minus 2 is 8. Ooh, minus, am I doing that right? Minus 18, so 8 minus 18, negative 10 plus 14 is 4, I think that's what we're getting. So you're going to have a minimum value at the point 1, 3, 4. The minimum value of the function is actually 4, but usually we go ahead and write the point in this case. So there is your minimum. All right, let's practice a few more before we get into absolutes. Find the local max and min values and saddle points of the function. Obviously, if they exist, there may not always be one of them, but you might be able to find at least one or two of these things. So let's take fx, which is going to be negative 2 minus 2x. And we have to set that equal to 0. We'll take fy, which is going to be 4 minus 8y, and we'll set that equal to 0. So in the first one for fx, if I add 2 and divide by negative 2, we get that x equals negative 1. And for y, adding the 8y over and then dividing, we get that y equals 1/2. So we've got a critical point at the point negative 1, 1/2. So we need to do our test. So we are going to need fxx, which in this case is going to be negative 2. We're going to need fyy, which in this case is going to be negative 8. And we are going to need fxy, which I guess I'll just put out here. And the second derivative with respect to y of x is also going to be 0. So what we get is our determinant is negative 2 times negative 8 minus 0 squared. So we get 16. Once again, that is greater than 0, indicating that we do have a critical point. So now we just need to check the sign of fxx. Fxx here is less than 0, which means that this is going to be concave down. That means we have a maximum. So we're going to have a maximum at the point negative 1, 1/2, and probably could do this one with it. Let me see. 9 plus 2 is 11. Plus 2 more is 13. Minus 1 is 12. Minus 4 times a fourth, so minus 1 more is 11. Just thinking I might have to use a calculator there, but I think we're good. All right, so that's it. I mean, that's how you do it. Now, are they going to get more complicated? Yeah, probably, because we're going to have to do some where it's not going to be quite as easy to find the x and y values. These have been relatively straightforward. Let's take a look at the next one. Find the local max and min values and saddle points of this function. So once again, fx 4x cubed minus 4y, we have to set that equal to 0, and fy is going to be 4y cubed minus 4x. All right, so this one's not going to be as easy to deal with because they both still have x and y in them. So what I'm going to do is I'm going to solve one of them for a variable that's easy to solve for. Doesn't matter which one you pick. In this case, I think I'm going to solve the first one, the fx. I'm going to solve it for y. So that means I'm going to get that 4x cubed equals 4y. Divide the 4's out, and you get that x cubed equals y. So what I'm going to do is I'm going to take that x cubed, because that's the value of y, and I'm going to plug it into that y right there. So now what we're going to get for fy is 4 times x cubed minus 4x. And that has to equal 0. I should put equal 0 up there as well. So now at least everything's in terms of x, and I can find the x value or values here. So we're going to get, that's going to be 4x to the 9th minus 4x equals 0. I can factor out a 4x, which leaves x to the 8th minus 1. So we are going to get that either x equals 0, x to the 8th, you can factor multiple times, or you can just say that x to the 8th equals 1. The 8th root of that, because it's an even root, is going to be the plus or minus 1. So we're going to get 3 possible x values here, which is going to end up giving us 3 possible y values. So we're going to have 3 critical points here. So our critical points are going to be when either x is -1, +1, or 0. So if x is -1, we can plug -1 into here to get our y value. So that's going to be -1 for y. We can plug in 0. That's just going to give us 0 for both. And we can plug in +1, which is going to give us +1. So we have 3 critical values. So this is where I say we're going to create a chart because it's just easier to do this. So typically your chart looks something like this: fxx, fyy, fxy, and then d. So we're going to do that for all 3 points. All right, so let's go ahead and actually find these things. We need fxx. So put that in red, I guess. So fxx, and remember that's coming from here. You start from there, is going to be 12x squared. At our point, at our critical values is what we're going to need to do. So I'm actually going to leave that alone for now. We're going to need fyy. Fyy is coming from here, so that's going to be 12y squared. And then we need fxy. So that comes from here, and that's just going to be -4. All right. And the good thing about fxy or fyy, once you square it, it becomes positive. So you're always going to be subtracting some kind of a positive value. All right. So at our critical points, the second derivative with respect to x, this one, 12x squared at the critical point -1 is going to be +12. At 0, 0, it's going to be 0. And at 1, 1, it's going to be +12. fyy at our critical points, once again, is going to be +12, 0, and +12. And that's just from plugging in the y values of our critical points. fxy is -4 in every case. There's nothing to plug it into. So remember that what you are doing is you are multiplying these, and then we are subtracting the square of each one of those to get our determinant. So the first one, we get 144 minus 16. I really don't care what the value is. You can write it if you really want to. all I need to know is that that is greater than 0, and fxx here, oops, is positive. And since fxx is positive, that means that it is concave up, so we've got a minimum. In our second one, 0 times 0 is 0, minus some positive number is going to be less than 0. There's nothing else to do when you get that. You simply know that you have a saddle point. If your d value is less than 0, it is a saddle point. And then the last one is going to be the same as the first one. That's going to be greater than 0. Once again, fxx here is also greater than 0, which means that we have a minimum. All right, and then obviously you could plug these things back in to find your minimum value. I'm going to skip that step for right now, just because I want to make sure we get through these next couple of pages within this video. All right. Use level curves to predict the location of critical points of F and whether F has a local minimum or maximum or saddle point at each of those points. Then use the second derivative test to confirm your predictions. All right, so if we look at what's going on in these level curves, what it looks like is, if I kind of look at how these curves are going perpendicular to the curves in this direction right here, I can see that the heights are increasing. It goes from 0 to 1 to 2 to 3.2, 3.7, all the way up until it gets to 4 right here in the center, and then it starts to go back down. Whoops, didn't mean to do that. So all the way till it gets to there, and then it starts to go back down. So likewise, coming from the other side, it's going from 3.2 to 3.7 all the way up to 4. So this is increasing until it gets to that point. But look what it's doing in the direction perpendicular from this side. I'm going from 6 to 5 to 4.2 down to 4. And then it's the same thing on the other side, because these level curves follow all the way around. It's going from 6 to 5 to 4.2 down to 4. So what it looks like is that it's increasing in the direction of the red arrows, but it's decreasing in the direction of the green arrows, meaning that this is most likely a saddle point. So it looks like at 0, 0, we have a saddle point. And this is our guesses right now. All right, so where else might we have something? Where else does it look like this thing might plateau? It looks like maybe around 1, 1, like right around there. We might have some kind of a plateau. So let's see what we've got going on there. So if we go again perpendicular to the level curves, in this direction, they are all coming down. Whoops, I keep hitting my eraser. They are all coming down, which means that from the other side, they're all coming down, because those are the same level curves if you trace them all the way around. Also, from this direction, it's the same level curves. Those are coming down. And we already know that if we go this direction towards it, it's coming down, since the red arrow was going up in the opposite direction. So to me, that looks like all those values are going from higher z values down to lower z values, meaning that I believe 1, 1, or somewhere in that range, would be a minimum. And then it says to use the second derivative test to confirm your predictions. That's not something I'm going to do in this video. By all means, go ahead and work that out and see if that works out for you. But I believe that those are indeed true statements. All right, got one more page here. This is going to be a slightly longer video, just because I want to make sure I get through this one before I go into the absolutes. So find the local maximum and minimum values and saddle points of the function f of x, y equals e to the x cosine y. All right, so you notice there's not a lot of space here, so that really should tell you something. Fx, the derivative with respect to x, is just e to the x cosine y. Fy is going to be negative e to the x sine y. All right, we need to set each one of these things equal to 0. The one thing I know is that e to the x can never be 0, so those are really irrelevant when it comes to this. So really this is going to occur when either cosine of y equals 0, or the one over here where sine of y equals 0. All right, well, cosine of y is going to equal 0 at every pi halves. So we know that y in this case is going to equal pi halves plus, basically you're going to hit every pi halves by a rotation of every pi. So it's n pi, or actually it's every odd n pi actually. So every odd n pi halves. Yeah, so every, I guess you would actually just be, I don't know why I did that. You would add pi to pi halves. Jeez, that was right in the first place. And then sine of y is going to equal 0 at 0, pi, 2 pi, and so on. So basically it is every n pi. Well, in this case, there is no way for us to add pi to pi halves and get any of these values over here, which means there is no overlap. These things will never equal each other. There are no values of these, there are no y values that these will ever be the same. And since the y values can never be the same, there are no critical points. Okay, this thing actually has none. Has no peaks, no valleys, no saddles. All right, and then the last one. Find the local maximum and minimum and saddle points of the function which is given here. Personally, I would choose to go ahead and distribute everything in here. You certainly could try and do it another way, but to me, distribution seems to be the easiest. So that's going to be foiling, that's going to be x. Inside is going to be x squared y. Outside is going to be y. Last is going to be x, y squared. Now we can take partials, and this one is not going to be pretty. So f sub x is going to be 1 plus 2xy plus y squared. That'll have to be set equal to 0. And fy is going to be x squared plus 1 plus 2xy, which will also have to be set equal to 0. One way or the other, I got to solve one of these things for either x or for y. I'm just going to go ahead and solve the first one for x. You could easily solve the second one for y. You don't want to solve for either the y squared or the x squared part because it's way too hard. So let's go ahead and solve this first one for x, which means we're going to get 2xy equals negative y squared minus 1. Divide both sides by 2y, you get that x equals negative y squared minus 1 over 2y. All right, that's actually pretty ugly to deal with, but that's what we have to deal with. So this is all going to get plugged into the x's right there. That's why I said this is going to be ugly. All right, so we get that fy now has to equal negative y squared minus 1 over 2y, all that squared, plus 1 plus 2 times negative y squared minus 1 over 2y times y equals 0. Okay, this one's kind of a mess. All right, so if you can come up with a shorter way to do these, by all means do so. The only good thing about the one over here is that that 2 cancels that 2, that y cancels that y, so that just leaves us with a negative y squared minus 1. But this one, we still have to FOIL that thing out, FOIL the top and distribute on the bottom. So we are going to get, let's see, first times first is going to give me y to the 4th. So minus y squared times minus 1 is positive y squared. I have to have 2 of those. And then plus 1 over 4y squared. Got a plus 1. Then we got minus y squared minus 1 equals 0. Looks like the plus 1 and the minus 1 are going to go away. So now we've got y to the fourth plus 2y squared plus 1 over 4y squared minus y squared equals 0. This is just not pretty. Got to combine these fractions. So let's see. You know what? Instead of that, I think I found maybe a slightly easier way. Let's go ahead and add the y squared over, and then I'm going to multiply both sides by 4y squared. So that'll give me y to the fourth plus 2y squared plus 1 equals 4y to the fourth. Let's get everything onto one side because this is definitely going to be something higher than a quadratic. So 0 is going to equal 3y to the fourth minus 2y squared minus 1. And luckily, believe it or not, this factors. So here we're going to get, it's going to have to be 3y squared and y squared. The factors of 1 are 1 and 1. In order to make that a negative 2, that needs to be negative. That needs to be positive. The 3y squared plus 1 can never equal 0. The y squared minus 1 will equal 0 when y is plus or minus 1. Long way to go to get to that point. So these are our y values. Now what we need to do is find the associated x values. All right. So let's go ahead and plug those y values back into here. I think that would be the easiest to find our critical points. So our critical points, let's see. When y is negative 1, if we plug that back in there, you're going to get negative 1 minus 1 on top. So that's negative 2 over negative 2. So that's positive 1. Your first x value is positive 1. When you plug in a positive 1 for y, you're also going to get negative 2 on top, but this time it's going to be over positive 2, so you should get negative 1. So those are our critical points. Okay, again, that was the hard part. That was the long way. The rest of this should be pretty quick and easy. So now we need fxx. Fxx in this case is 2y. We need fyy. Fyy in this case is 2x. And we need fxy, which is going to be 2x plus 2y. All right, so let's go ahead and set up our chart. So we have fxx, fyy, fxy, and d. We need to do that at the points 1, negative 1, and negative 1, positive 1. So fxx at 1, negative 1 is going to be plugging in the negative 1 for the y right there is going to give me negative 2. Fxx of our second point is going to be positive 2. Fyy, so now we're using that one, plugging in the x value is going to give me positive 2. Fyy of the second one is going to give us negative 2. And then fxy, and the nice thing about fxy is if you plug in 1 and negative 1 for x and y, you're going to get 0 in both cases. So remember, it's fxx times fxy minus the square of xy, but that's going to be 0 in both cases. So in the first one, we get that our d value is less than 0. And in the second one, we get that our d value is also less than 0, which means both of these create saddle points. And again, I know this video is running very long, but just to make sure you understand a saddle point, so you want to think of it in some kind of a three-dimensional space. Oops. Come on, erase for me. There we go. In three-dimensional space, something is a minimum like this, but then coming from a different direction at that same point, it's a maximum. So it's not easy for me to draw. This is one of those things right there. and it's the direction that makes it difficult. This is one of those things that if you think back to your hyperbolic paraboloid, the really difficult ones to draw, or something that actually looks like a saddle, like a Pringle chip, if you can picture that. If you can picture the way a Pringle looks like in like your X direction, it would be a minimum, and in your Y direction, it would be a maximum. So it looks just like a saddle, which is why they call it a saddle point. All right, extremely long video. Unfortunately, the next one, because it's absolutes, will probably be a relatively long video as well, but that will be 14.7a.